In this video, we are going to continue our discussion of section 5.2, base 2 and base E. Basically, there are only two things we're going to cover in this video. The first, we will look at applying the compound interest model, or rather we will revisit it since we've seen it previously. Secondly, in order to do objectives 5 and 6, to work with the continuously compounded model and the general exponential model, to accomplish objectives 5 and 6, we will have to have base E. And so we're going to look at a number of the logarithm rules and the exponential rules, specifically using base E. And then in the future video, we will actually look at objectives 5 and 6. So let's start with remembering the compound interest model that we've seen before. We know that the amount in the future, or the amount at some time t, can be calculated by taking the initial principal p and multiplying it by this quantity 1 plus r over n, where r is your annual percentage rate expressed in its decimal format, n is the number of compounds per year, and you'll take that to the exponent nt. And so the first of our three examples, how long does it take $4,000 to quadruple in value when you invest it at 8% compounded monthly? Well, of course, we know our model. I have that backwards. It's A. Oh, come on, eraser. You're killing me here. Okay, so we had the principal in the future. Oh, I did it again! The amount in the future is based on the initial principal. All right, so let's start putting in the pieces that we know. What is the initial value? We're starting off with $4,000 to begin with. And if that value quadruples, it's going to give us $16,000. What is your interest rate? Well, 8% is 0.08. Compounded monthly gives us 12. And so we have 12 compounds times the number of years. Of course, I rushed through that because we are already very experienced with identifying these pieces based on our earlier work. The only difference now is we have to solve this. We'll note once again, where is the variable? The location of the variable tells you what strategies you need to employ. And because it's in the exponent, as you noted, Brian, it tells us we will have to take a logarithm. Before we get there, though, I'm going to divide by the 4,000, which would have told us 4 for the quadrupled value. And then we have the next part of our equation. Now what? This is where we'll take the logarithm. And our whole reason for taking that logarithm is so that we could apply the power rule. We keep seeing how useful this power rule is. After taking the logarithm, we are allowed to bring down that exponent and turn it into multiplication. What would we need to do to solve now? Well, we can divide about this multiplication. And that would cancel out. What else could we do? What else do we need to do? Absolutely, we have to divide by 12. And after the multiply by 12 and divide by 12 cancel each other out as inverses, we have t is equal to a whole bunch of stuff that we can put into our calculator. the logarithm of 4 divided by the logarithm of blob divided by 12. Alex, you said you have it, so what is it? And the students are telling me after rounding answers using their calculator, they obtained 17.4. 17.4 what? How is time being measured? It's years. So there you go. At 8% interest, compounded once a month, it'll take you 17 years to quadruple your money. Well, let's look at it the other way. What if you're not investing money? What if you owe money for something like student loans or credit cards? How long would it take for your debt to double if you were charged an 18.99% interest rate compounded daily? And by the way, credit cards all do daily compounds. They always do it. And an almost 19% interest rate is pretty common for your first credit card because you don't have a credit history, so they kind of screw you over. Well, let's actually run through it. The amount, principal, 1 plus r over n. What information are we told? Okay, we're told the interest rate. How about the number of compounds? Assuming that we have 365 compounds per year. So we're ignoring the fact that there are leap years. And then what about A and P? Well, we don't know them, but we know that it doubled, so basically it's 2 and 1. The same way that last time when we had a quadruple, it turned out to be a 4. 4 for quadruple. Well, if we're doubling, it's going to turn into a 2. So let's solve it now. Are you comfortable if we skip some of the steps in the writing? Or do you want me to show each one? Okay. The two steps I'm combining right now, taking the logarithm and bringing down the exponent, I'd have the logarithm of 2 equals 365t multiplied by the logarithm of this blob. Then what? What do we have to do to isolate the t by itself? What did we do last time? We divided by the logarithm of that blob. And yeah, you love my accurate math by writing down blob. And then we also divided by 365. With those two pieces, we know what we'll have to type in the calculator. Logarithm of 2 divided by the logarithm of this blob, 1 plus 0.1899 divided by 365, then divide by 365. After putting it into our calculator, what did you obtain? So after pausing the recording and putting it into my calculator, here's what I obtained. And so we have then, oh crap, I forgot what number it was. 3.65. 3.65 years. So basically, you get a credit card, and if you don't make your payments in a little bit under 4 years, basically 3 years and 8 months, you now owe double the amount of money that you had originally. Here's our last example. for compound interest. Money compounded monthly grew from 8,000 to 14,000 in 3 years. What's your annual percentage rate? As always, we need to start putting in each of our values into the formula. And so we had 14,000 in the future, 8,000 for the initial principal, 12 compounds per month, and 3 years. Thus, this is a problem where we are not looking for the time, we're looking for the rate. Where is the variable? The variable is a part of the base. It's not in an exponent. Because the variable is not in the exponent, we will not use a logarithm. We don't need a logarithm. Logarithms are used to figure out the variable in an exponent only. What we'll do instead, we can divide by 8,000. And after dividing by 8,000, we have the fraction 7 over 4 equals r over 12 to the 36th power. And we're actually back like the type we were doing in our last unit. How do you get rid of an exponent of 36? By raising it to another power, the 1 over 36 power. We know a power raised to a power, we have to multiply them, and those reciprocals cancel out to 1. And so we have r divided by 12 equals 7 over 4 and 36th power. Obviously then, our next step is to cancel out the divide by 12 by multiplying. After that stage of multiplication, we have precisely what we could type into our calculator. So let's get our calculators out, type it in. I see people in class are already going at it, so what did you get? And I've had multiple students confirm they're getting 12.2. So what is this 12.2? It's a 12.2% rate. Although we finished the examples for the compound interest, we still need to create some formulas specific to base E. So you remember all these notes from last week? How we looked specifically exponent rules emphasizing power functions, and we could take the same facts and write them as a base 10 exponential. We also saw that we could take those exact same rules written as an exponential format and instead write them as a logarithmic format. This is what we want to do today as well. The last things we are going to do for this video are rewrite a number of these rules. Instead of using base 10, we'll rewrite these exponentials and logarithmic rules using base E. All right, so let's start at the top here. Please notice the format we have. Base E, and remember E is a number that's about 2.718. It keeps going like the number pi. In a future video, we will actually look at why are we using base E? Why is it such a big deal for us? But before we look at the reasons why, we want to gain some familiarity with what. What should come before why? And so how would we rewrite this in its logarithmic form? Well, log base E of y equals x. fairly unusual to write down log base e. Instead of using log base e, it's far more common to simply write down ln, which stands for the natural logarithm. And once again, in our future video, we will talk about why base e is natural. But basically, it's very natural to calculus, and we will see why later. Let's go to the second one. We saw earlier that 10 to the log power, what did they do? They canceled each other out. Well, e with the natural log, they cancel each other out, giving us just x. Thus, this piece looks like this. With that exponential rule, how would we write that in its logarithmic form? Consider our rule. We saw before that, and it's located. Basically, this problem here was focused on the idea that e and natural log cancel each other out. So we'd like to see, how does e and natural log cancel each other out? Well, natural log of e to the x, as we noted, natural log and e cancel, leaving you with just the x. The same way that we saw that base 10 and base 10 logarithm cancel, base e and base e logarithm cancel. Let's look at our next rule. E to the x times e to the y. What's the shortcut when you multiply? What do you have to do to the exponents? You add. So, like before, we saw that rule here. Instead of having base 10, we're using base e. And so we're going right back with the same type of a rule. It's the same rule, just written with different variables. We would have a natural log of x times y gets split up using addition. Similarly, moving to the next line, our rule was to subtract the exponents. That rule rewritten in its logarithmic form, if we have a quotient, we'll split it up by subtracting the logarithms. Progressing to the next line. Earlier we had 10 to the 0 power. Well, what's anything to the 0 power? 1. And so, in order to write this in a logarithmic format, we would say the natural log of 1 equals 0. Consider the negative exponent rule. How do we handle negative exponents? A negative exponent means 1 over e to the x. To write this in its logarithmic form, log of 1 over e to the x, this would simply equal the opposite of x. And lastly, a power raised to a power had the rule for multiplying. Well, if we take the natural log of e to the x to the y power, it's simply equal to x times y. For this last rule, we could generalize it a little bit further and note, if we were to take the logarithm of a constant number raised to the x power. Think of our power rule. This would equal to x multiplied by that logarithm. Last two things worth noting. Last pieces we have to consider. E to the x has the domain. Well, remember what its graph looks like? The graph of e to the x looks like this. So what are the x values that work? All of them. E to the x has the domain of all real numbers. Every x value can be plugged in. But what about its range? For the range, we don't get anything on the x value because anything on the x-axis because of the horizontal asymptote. We also don't get anything underneath. That tells us the range goes from 0 to infinity. Since natural log is the inverse, and inverses simply work backwards, these two things get flipped. Natural log of x has a domain from 0 to infinity, and it has a range of all real numbers. And thus we finish up our study for this video. In the next video, we will take these rules that we've just developed for the exponential model, and we will look at how to create the continuously compounded interest formula. And then we will also see how to apply the general exponential. Basically, we're going to go we'll do the half-life and the doubling time model. We'll do the compound interest model. We'll do all those same objectives, but instead of using a base 2, a base of 1/2, we'll instead use base e to do the same kind of work.